Okay, so today we are going to finish talking about suffix trees and suffix arrays. And next week on Monday, we are going to start talking about profiles, hidden Markov models. First, we are going to start with hidden Markov models, and then we are going to see multiple sequence alignment techniques. All right, so patterns, profiles, and multiple alignments will be our next week's topic after we finish suffix trees and suffix arrays today. So if you remember, we described suffix trees on Monday, and it was a tree of suffixes of a string that helps us to carry out pattern searches very quickly. The way we search these patterns is that if let's look at an example suffix tree here. For example, this is a suffix tree for the string xab, xac. If you're looking for a pattern bx, for example, does bx occur as a substring of this string? If it's a substring of the string, which means that if it occurs somewhere in the string, it has to be a prefix of one of the suffixes. If we have a tree of all the possible suffixes, any pattern that exists in this string should be a prefix of some suffix. So the way we search for bx is we simply start from the root node and try to match the characters of the pattern one by one. Since each edge coming out of an intermediate node starts with different letters, it will give us a deterministic, unique way to follow the letters of this pattern. So we are going to start with B, and along the edge we'll also be able to match the second character X, and at that point we know that, oh, okay, BX exists in this string, and it's actually a prefix of the third suffix. So wherever we stop our search, maybe in the middle of an edge or at an intermediate node or at a leaf node, wherever we are, the subtree, all the leaf nodes below that place where we stop our search are the list of suffixes that contain this bx as their prefix, because all these suffixes, as you can see, they will be spelled out by concatenating the edge labels starting from the root node. Okay, so xab, xac, for example, is this one. There's also an xac. So this xab, xac, which is the entire string, and xac, which is this fourth suffix, 1, 2, 3, 4. Let me change the mouse pointer size. This one, as you can see, the fourth suffix is 1, 2, 3, 4. Fourth suffix is xac, is also, they share the same path, that the path part that starts with xa, so they share the prefix xa, so therefore part of the path is that shared edge between them. So if you're looking for the pattern xa in this, for example, we are going to follow this path, stop our search here, and below this point we are going to see that the subtree contains two leaf nodes, 1 and 4. These are the places where our pattern xa exists. So in order to make sure that we have all of the suffixes represented as leaf nodes, so that's the answer to this question, does a suffix tree always exist? When a suffix is a prefix of another suffix, in the case of this, for example, xab, xa. Xa here is a suffix by itself, but it's also a prefix of this xab, xa. And therefore, if you look at this tree, xa, this suffix is going to end here, and it is not represented as a leaf node. We either need to have an edge label with empty string on the edge label and put this 4 here as a leaf node, and otherwise we have seen last time the way to solve that is to have a character that doesn't appear anywhere in the string. If we have that as our last character, we ensure that no suffix is a prefix of another suffix, so therefore we can have all the suffixes as leaf nodes. For example, in this example, if we have dollar at the end, we have xa here, that xa dollar will be that fourth suffix, and as you can see, it's represented as a leaf node by itself. There's we also talked about the construction algorithm, The construction algorithm that we have seen in class was a quadratic O(n) square time complexity algorithm, and by inserting each suffix one by one to an intermediate tree that to the tree that we are building, we construct the entire suffix tree. So what we are going to do is we are going to start inserting suffixes by starting the entire string, which is the first suffix, and then the second and third one. Each of them end with the character n. What we are going to do is we are going to follow the matching algorithm for a suffix. We are going to try to match its characters one by one, starting from its ith character from the root node. As long as we match characters, we follow that path along the edge labels. And at some point, there's a mismatch bound to occur. Okay, a mismatch is bound to occur along this path because no suffix is a prefix of another suffix, right? Therefore, which means that at some point there will be a mismatch when you're searching for a suffix in your path. You're going to encounter a mismatch. If no mismatch occurs and you match the entire characters, it means that a previously inserted suffix into this tree is actually containing this new suffix that you're about to insert as a prefix. So, but that's not going to happen because we make sure that we put this dollar character at the end. And at the time, in the first place, when the mismatch occurs, that's where we need to put our new suffix. It's going to have its own path. And we break from the edge label at that point. It may be in the middle of an edge, label. In that case, we introduce a new node by breaking the edge label into two parts. At that point, a new intermediate node. If the mismatch occurs at an intermediate node itself, because it may be the case that, for example, let's look at. Imagine you want to insert XAC here. Imagine, this is not part of the suffixes, but imagine we try to insert XAC dollar to this one. So as you can see, when we try to add XAC dollar, after XA is matched, the mismatch occurs at this intermediate node. We cannot follow any outgoing edge labels because the third letter in XAC is C. Therefore, we need to insert a new edge coming out of this intermediate node. But if we try to add, for example, XB to this suffix tree, partially constructed suffix tree, if we want to add XB, the mismatch is going to occur in the middle of an edge. And at this point, we have to break this edge into two parts, X, that one part going towards A, the other going B. And this is where we introduce a new intermediate node during construction. There is a nice website, maybe you already know that website, which is called Visualgo, which contains visual descriptions of some algorithms. I'm going to write it in the chat box, visualgo.net. It's actually maintained by a person who is very well known in the competitive programming domain. Stephen Hallam, and these are his books on competitive programming. There are really nice visual representation of different data structures, like visual representation of sorting, linked list, hash tables, graph structures, union find data disjoint set, data structure, binary search trees, and one of these data structures here is suffix tree. So if you click on suffix tree, link here, you'll see that the suffix tree is built for some string here. What is the string? Where is the zeroth suffix? Can we move in here? So let's actually, we can build a suffix tree for another one, for example, bananas. If this is the suffix tree for bananas, it's it doesn't show one by one, step-by-step insertion procedure. It's an instant suffix tree creation, but you can, for example, search for Anna in bananas, and it's, I think, going to show it step by step as you go over the pseudocode how Anna is found. You can change the speed you can, so how do we start this? We can go step by step. Consider the current vertex. We try to match, we look at all the outgoing edges until we find the one that contains an edge label which starts with A, the current letter. The current letter currently is A, and we find A here, we match, and we can continue. There's a partial match, so we can continue deeper. And therefore, we first look at this edge. It starts with dollar. No, that's not the one we are looking for. We continue, and this edge contains N and A. The match is a full match is done. It's complete. So banana, Anna actually occurs in two places. In the first, as a prefix of the first suffix. By the way, the suffix indexing is starting from 0. Therefore, the first suffix here is the ananas, and the third suffix here is anas. All right, so if it's found in two places, and the search ends here. If you're searching for something that doesn't exist, for example, in bananas, the term aba doesn't exist. So when we try to search for it, we go over, we look at, there's a match at A, but there's no match, no edge label starting with B here in this node. Therefore, it's an unsuccessful search. The keyword ABBA doesn't exist here. It's not found. But you can try to build your suffix trees for different letters. For example, you may give some DNA sequence. The one limitation of this website obviously is because of the view limitations, size limitations. You cannot write very long sentences. You are, I think, limited to 10 characters or 11 characters at most, 10 including the dollar character at the end. So if you try to build a suffix tree for this one, AACGCA, GCA, GA, it looks like this. All right. As you can see, we are going to have at most 4 outgoing edges, actually 5, including the dollar one. I didn't have any T here. If I had the base nucleotide T here, it will be another outgoing edge from this root node. And the branching factor is alphabet size plus 1. All right, so this is that suffix tree for that. And whenever we're looking for any pattern, we will just be able to search the pattern proportional to the length of the pattern. Your index size may be very long. It will be the entire string, but searching in the suffix tree is going to be very fast if you're searching for a pattern. You don't need to do a linear search over your entire string. Okay, this is what suffix tree provides us. So you can try different things in this visualgo.net. Let's continue. We have talked about the construction algorithm. This is a more formal description of that construction algorithm. But the example construction, I'm going to skip this part. Or yeah, we can. If you look at this XAB, XAC dollar, if you're going to insert this, we start with the first suffix. The second and third suffixes, they can be inserted directly because they each start with different letters. When we come to the fourth suffix, which is XAC dollar, we matched its characters, and then we split this edge at the first mismatch. B and C are mismatching, and we introduce an intermediate node, and the mismatch part becomes a path on its own for this new suffix, and the suffix 4 is inserted nicely. Then AC dollar, again, when we try to insert AC dollar, there will be a match in the middle of this edge. A is matched, and B and C are again mismatching, and we get ourselves another, so the mismatch is here, C dollar, fifth suffix here, and this one here. And C dollar is inserted, and dollar is inserted nicely. So this is how we can construct suffix trees in ON square time. As I said, there are extensions, it's improved. The suffix tree construction is possible to do in linear time. So there are more complex algorithms that allows us to build these suffix trees by making use of certain common parts of the string and avoiding building it again from scratch. So there's a linear time construction of suffix trees. You can search for on the internet for that linear time suffix tree construction. Will get you to Ukenan's algorithm. So this is it was in 1995. I think the paper is here, online construction of suffix trees. So online construction of suffix trees mean that dynamically, since if you have a very fast suffix tree construction algorithm which works in linear time, you can use it online dynamically as the string changes. The naive implementation is this one, O(n) square. We don't have NQ time algorithm actually. Ours is the one that I described in class is O(n) square time algorithm. So this Ukenan's algorithm is a linear time algorithm proposed by Esko Ukenan in 1995. Okay, so if you're interested in using suffix trees in your research, you can use this implementation by Ukenan to get it in linear time. So especially for large strings like whole genomes, if you want to build, if you want to search for patterns in whole genomes efficiently, and you believe you're going to do pattern searching a lot, if you're just going to search a single pattern in the whole genome, there's no need to construct a suffix tree for that. The main utility of suffix trees is that when you're going to conduct many pattern searches, patterns may be dynamic changing, and you're going to conduct many such searches, constructing a suffix tree over your whole genome. And the constructed tree will be your index structure, which can be used to make these fast queries. Okay, so ours is O(n) square complexity. The space complexity seems to be O(n) square if you have edge labels like this. If you repeat the entire edge label on each edge like this, the summation of letters, the total number of letters on the edges will add up to O(n) square. But there's a very simple way to reduce this to O(n) by instead of, do we really need to write edge labels like this with all the characters? They're actually we just need 2 integers to write on every edge label. Each edge label is a substring. Therefore, we just need the beginning of the substring, the index of the beginning of that substring and the end. So if we just replace these actual labels, which are strings, with just integer indices of those substrings, it will lead to a linear time space complexity. Okay, so yeah, this is what this slide is about. We can store edge labels efficiently, and this will reduce the space complexity to O(n). You may argue that it's actually O(n) times the alphabet size, because we haven't discussed the alphabet size here. We just considered the alphabet size itself as something constant. For DNA sequences, it's just 4. The nucleotides, number of different nucleotides is just 4. Therefore, 4 times n is just also O(n). We took it as a constant. For protein sequences, it's still a constant, 20n. The alphabet size is 20. It will be 20 times n. You may again think that it's linear, but the constant factor in terms of that in front of that linear term is quite large. If it was n log n, for example, log base 2 of n, if it's 20, is going to be a very large number. So you could as well have an n log n algorithm in that case. I mean, without no constants. Okay, but this is just a way to actually reduce. Oh, the space complexity is, let me repeat that again. The space complexity is quadratic in the case where we store edge labels as strings, substrings themselves on the edges. If you look at the paths, each suffix is a leaf node, right? Therefore, the quadratic complexity comes from the fact that if you want to store this tree as a tree with the edge labels as characters like this, for each suffix you're going to require I characters, or n minus I plus 1 characters. If you have a string of length n, for the first suffix you are going to need n characters along that path. And actually, some of these edge labels are shared. You're going to need another, for example, you don't need actually exactly 4 characters, or or 3 characters for this one, because part of it is shared. But if in the worst case, we may need to repeat lots of strings, substrings on the edge labels. So their summation, therefore, the summation of numbers from 1 to n is going to give us n square, okay, the O(n) square. Now, what makes this quadratic is the fact that we use, for example, 5 characters on this edge label. So the way to reduce the complexities, 5 characters, in some cases there will be more than 5 characters. So that's the part that increases the complexity, the quadratic. But if you look at the number of edges on the tree, okay, forget about the edge labels. If you just take a look at the number of edges in the tree, if this was a binary tree, okay, or for example, make it a ternary tree where we have at most 4 branching, when the branching factor is at most 4, okay, the branching factor of this tree is 4. Now, actually the analysis would be easier if you just think about the binary tree case, but in the case of 4, let me ask you this. If I have, in the worst case of a full ternary tree, fully balanced full ternary tree, if I have n leaf nodes, how many what is the total number of nodes in this tree? Okay, this is what I'm asking. What is the total number of trees in this tree, total number of nodes in this tree if I have n leaf nodes? In the case of binary, if this branching factor is 4 is complicating, think about the binary tree. If you have a binary tree, branching factor of 2 every time, if you have n leaf nodes, what is the total number of nodes in the tree? It's going to be 2n minus 1, right? It's like if I have this, it's like n plus, I will have n over, if it's fully, I will have n over 2 nodes in this level. I will have n over 4 nodes at this level, and I will have 1 node in this level. Okay, if you sum them up, so it's the height of the tree will be log base 2n, but if you sum all the leaf nodes here, 1 plus 2 plus 4 plus, for example, 2 to the n, what is this equal to? It's equal to 2 to the n plus 1 minus 1, right? So the summation is equal to that. Therefore, if I have n leaf nodes here, the summation of all the intermediate nodes up to n, if this n is obviously is going to be a power of 2, if you have a full tree of binary full tree, n is going to be a power of 2 here, and therefore the total number of nodes in this case will be 2n, which is also linear. Okay, or 2n, you forget the constant in front of it. Similarly, I think it's if you have in the case of branching factor of 4, still the number of leaf nodes that are here still going to be a constant factor of the number of leaf nodes. Okay, so now this time we're going to be even reducing it more. Oh, actually, it's not going to be. If maybe it's going to be even less than 2n because the height of the tree is going to be less that case. Okay, but in any case, the number of leaf nodes. But if the number of leaf nodes in a tree is n, the number of nodes in the entire tree, total number of nodes in the entire tree is also linear. It's O(n), which means that if it's a tree, what about the number of edges? If I have O(n) intermediate, the total number of nodes in a tree is O(n), the number of edges in the tree is also O(n), because if there are n nodes in a tree, there are exactly n minus 1 edges. Therefore, the total number of edges is also n. So in other words, if you just consider the number of nodes and number of edges as your space complexity, it's going to be linear. Okay, so this is how it is reduced. I mean, what makes it quadratic was each edge label could contain a long string. That was what making, in addition to the nodes and edges themselves, we are to store edge labels, right? If edge labels can be arbitrarily long, like substrings, this will increase the space complex. This is the thing that increases the space complexity to O(n) square. Exactly. We don't get rid of the edge labels. We make them constant space. What is the, for example, if for each edge, if I store just two integers, if each edge is cost two integers, what is this going to do? A constant factor times number of edges is going to be linear. We don't get rid of edge labels. We make them not arbitrarily long. We make them constant size. If you store constant things with edge labels, so what are these two integers that I stored at the edge labels? I and j, because each edge label is a substring of the original string. So for each edge label, I store I and j, so it becomes constant. Therefore, we get our edge number of edges is O(n). The space that I'm going to require for the entire edge is going to be a constant size. Okay, so for example, if two integers is 8 bytes, it's going to be 8 times n. You're going to be needing 8 times m bytes for your edges, which is linear complexity. All right, so this is how we can reduce it also to the space complexity, to linear one. Although the constant factor may be large. But in any case, it tells you that the index size, when you build a suffix tree for a genome, it may be 2 times the size of your genome, 3 times the size of your genome. If you use compression, you can get better. But it means that the size of your index structure grows linearly with your genome size. It doesn't grow quadratically. If it grew quadratically, if the index structure was growing much quadratically compared to your genome size, it would make it prohibitively expensive for whole genomes. All right, so this is what we usually look for in index structures. In terms of space, they shouldn't require too much space. They should be index structures that are linear, like on the size of the original data, is going to give us make it practically usable when we want to build index structures using those techniques. All right, let's get back to this one. This is the how we reduce it to O(n). Reduction of the time complexity to O(n) is more complicated. That's the Buchanan's algorithm. We are not going to cover it in this course. And this link probably is outdated. For suffix tree visualization, I suggest you go to this visual algo. So the substring L is shared between algorithm and visual. So this visualgo.net. So you can try to create your own suffix trees and see how the suffix tree is going to look like. All right, and as I said, there are suffix trees, their extensions, finding the longest common substring of two suffix trees. For example, we build a suffix tree for the concatenation of those strings, which is called the generalization of suffix trees. We can build a suffix tree not for a single string, but if you concatenate all these strings one after another and try to build a suffix tree for them, their share parts, if those multiple substrings are sharing, multiple strings are sharing a pattern in them, they will all be visible as a shared path from the root node. So we can use it to find the longest common substrings also. We can also use it to find things like that are specific to individual strings. So it's like the inverse problem, not the inverse problem, but a different problem. Instead of finding the longest common substring, imagine I'm asking you to find unique substrings to a group of 10 sequences. If I give you, for example, 10 DNA sequences, and I'm asking you to find substrings of length 20 that are unique to each of them. What you can do is, again, you can build a suffix tree for the concatenation of those three. And meanwhile, while you're building it, you have to mark the endpoints. For example, the first string covers maybe the region from 1 to 2000, then from 2000 to 4000 your second string comes, but you can identify them by the suffix IDs. So what we will do is, from the root node, you can follow a path. If there is a certain subtree which is just composed of suffixes in a certain region, for example, from 1 to 2000, if all the suffixes in a subtree are coming from those leaf nodes, they belong to the suffixes from 1 to 2000, it means that the path until that point is a unique edge label to that first string. Okay, so you can find unique strings as well by using these suffix trees. So it's really useful. The generalization of suffix trees have very useful applications. Also, when we are doing the running and searching time, we didn't think about this in the alphabet size. As I said, the alphabet size also comes as a constant factor. And also, if you're finding whether a matching exists is linear in the time, this is the size of your pattern. If you want to also figure out all the occurrences of a pattern in your string, you may need to spend additional k time, where k is the number of occurrences and p. And it has nice for very large problems. A linear time and space bound sometimes may not be good enough. Sometimes the constant factor in front of the suffix tree may be prohibitive for very large sequences. For example, instead of requiring 8 gigabytes, if you, again, it's linear, 8 times 8 gigabytes is 64 gigabytes. If you cannot afford that 64, you may need to, even sometimes, what I want to say is sometimes that constant factor is practically important, even if it's double the size, quadruple the size, even if it's constant, it may be prohibitive for certain practical applications. Therefore, there are also variations of suffix trees like suffix arrays, which are really, really efficient. I'm going to talk about suffix arrays as well until the end of the course today. It's really simple. The idea is really simple, actually. There's also the alphabet size. As I said, we ignored that. It comes as a constant factor to that. And I talked about generalization to multiple strings. The way we built the suffix tree in such a way that from any node we can find an edge in constant time for any specific character in the alphabet. So while we are doing the searching, remember when I not this here, but let's take a look at, while we are doing the searching, we assume that, for example, from the root node, if I'm searching for the pattern CAC, imagine I'm searching for the pattern CAC. So from the root node, I assume I immediately find the edge that starts with C. It actually takes some time, right? First, I want to look at this edge, then come to this edge. Oh, this edge starts with a C, and let's continue CAC on this path. So every time you're looking for which edge starts with a C, you're spending some time which is proportional to the alphabet size. One way to avoid this is to have an array of child nodes in which C is always going to have a specific location in that list of childs. For example, if you just have ACGT, so you can actually have an array of child nodes, an array of children, descendant nodes of an intermediate node. In that case, you're always, in order to figure out whether there's an edge that starts with a C, you always look at a specific position. For example, the first position in that child list always denotes C. You immediately go there and see whether there's a subtree leading out of that position. If it's null, it means that there is no edge that starts with C. You may also implement it like that. So that's an implementation issue. But in that case, if your child list is not dynamic like this, if you have a fixed positions for each of them, there's another drawback of that, which is you may be wasting storage, because for edges that do not exist, you have to reserve space for them. So this actually increases the space complexity this time to m times alphabet size space. Okay, because if you have fixed arrays, regardless of whether you have an edge coming out of that or not, for each intermediate node, you're going to be spending space that is size of your alphabet. So it may increase the space, but since this alphabet size is constant, this still is constant complexity. So this is when m is the size of the string that you're building for. There are some more compact representation of suffix trees, but I'm going to skip those. I talked about generalized suffix trees, how we can build a single suffix tree by concatenating multiple strings together. This longest common substring, for example, we can build a generalized suffix tree for S1 $1 or some other symbol, and S1 $2, some two symbols that are different, which do not exist in any of these. And we can mark every internal node of the tree with 1, 2, or 1, 2, depending on whether we arrived at that intermediate node by following a suffix belonging to the suffix that starts with the first string or starting with the second string. Okay, and finding the internal node, which is labeled by both 1 and 2 and has largest edge label depth. I mean, it has the longest edge as we move from the root node, is going to give you the longest common substring. Okay, it means that if this is a path from the root node, which is shared by both the suffix that belongs to 1 and 2, which means that that substring is shared, that prefix is shared by both 1 and 2, that makes it the longest common substring in both of them. For example, if you try it with pessimist and Mississippi, you're probably going to find this SSI, I think, is the longest substring, right? SSI is going to be the longest substring. So when we are inserting this suffix, SSI, and when we are inserting this suffix, which is belonging to the second string, they are both going to share this SSI from the root node. And that intermediate node that ends at SSI is going to have both labels 1 and 2. And this is how you're going to find the longest common substring. This is another use of suffix trees for a different problem. This is like that inverse or negative problem of the same thing. Instead of finding common things, we may sometimes in biology, we may be looking for unique things for sequences. Especially when we talk about microarray chips, we are going to see that. For microarray chips, when we are designing microarray chips, we need to design small sequences that are signatures, that are unique to a certain gene or a transcript. And finding those can also be established by a generalized suffix tree. So this is like, I think from the abstract of that paper, you can also take a look at of this to see another utilization, another use of suffix trees in bioinformatics. Okay, suffix arrays, that's the last thing we are going to talk about today. It's really simple actually. It's data structure is just an array of suffix IDs. The suffix, it's a sorted array of suffixes. The suffix arrays were introduced by Member and Myers in 1993. They are more space efficient in terms of not asymptotic complexity. They are both linear. This one is also linear. It's not sublinear time, but the constant factor of suffix trees, suffix arrays is much lower than suffix trees. A suffix array of a string of x of length m is basically an array of m integers. We just store integers, single integer per suffix. And the array will be sorted with respect to the lexicographic order of those suffixes. Here's an example. Look at this suffix array. The middle part here that is shown on this slide is only for visualization purposes. Okay, the actual suffix array is this. So this is your suffix array, which just contains the number. So, and this is the index of your array. So you get an array of 11 integers. If you get it, so a suffix array here basically is an integer array. Let's call it suffix array of size 11. This is my suffix array. And suffix array 0 contains this single integer 3. Suffix array 1 contains 4, 1, 2. So these are the integer numbers that are stored in my suffix array. But what are these numbers? Let's take a look at them. What is 3? What is 4? What is 1? 5, 11. So these are the suffix indices. This means that in the lexicographic order, the third suffix, which is 1, 2, 3. So this is the third suffix. Third suffix starts from here, A, 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 C, A, T. So if you sort the suffixes, and by the way, you can, therefore, the construction time is n log n. So that's one drawback of suffix arrays over suffix trees. Suffix trees, remember, you may construct suffix trees in O(n) time, linear time, but O(n) log n is not that worse than O(n). So in order to sort these suffixes into an array like this, you need to spend n log n time. You cannot do it faster than this because if you're sorting it by comparison. So that's the lower bound for sorting, comparative sorting algorithms. All right, so if you look at this, this is we sort these suffixes. These are strings. We are sorting strings using their lexicographic order, meaning that if somebody gives you two strings, ACTAT or CATAT, dollar, which one would appear first in the dictionary? If you can answer that, and you can answer that. The thing is, if they start in the same letter, we look at second characters. If they have the second same letters, we look at the third characters. Here, their third character is A, this is C, therefore this one comes first. And they're, again, bound to differ at some character, right? So no two strings, no two suffixes are equal to each other. They're all different because of this dollar at the end. And therefore, we are going to have a mismatch at some point during this lexicographic ordering. This one comes before. Third suffix comes before the fourth suffix. And then this is the first suffix, fifth suffix, seventh suffix. So this one gives us a sorted order of suffixes is our suffix array. All right, then how can we use it for pattern search? We are going to, again, pattern search, unfortunately, if we have a pattern of size n, we would not be able to perform this search in OM time. Suffix arrays have disadvantages like, a little bit longer, slower construction time, but all these drawbacks are, you can tolerate these drawbacks because of this very efficient space complexity. Okay, it's just an array of integers, nothing more. And also the search time, I was talking about that. The search time is no longer OM, but the logarithmic factor of the database size comes into picture. Because the way we are going to search patterns here is this. For example, if you're looking for a pattern CAC here, what you're going to do is this. First, you're going to search for the first character and identify by binary search. You're going to do a binary search. For example, if you look at the middle of this array, you see that it starts with an A, right? Therefore, CAC, the pattern CAC, cannot occur in the first half of this array. It has to be somewhere in the second half. So we divide it in binary search. We identify, C has to occur here. So you look at, again, the middle by dividing your search bound by half each time and looking at the middle, you find the interval. This is not like regular binary search because at the end we are going to not pinpoint locate CAC, but find the interval where C occurs. For example, here C occurs in the indices between 6 and 7. Okay, So by binary searching C here in this list of arrays in log n time, I'm going to perform maybe 2 binary searches for upper and lower bound. I'm going to find this interval 6 to 7. So all the characters from suffixes from 6 to 7, they start with a C. And then I'm going to perform another log n times search for the, so it's going to be actually log n times m times log n. Another logarithmic factor is coming to our search. And then I'm going to search for A to see whether CA occurs in which range within this 6, 7. The range is always going to get smaller and smaller. We'll see that A occurs as the second character in both of them, or so it still stays 6, 7. And then when I'm looking for the C, again, I'm going to go in the middle because these are sorted. I mean, the third characters are also sorted, right? Because if we sort them as they appear in the dictionary, if the first 2 characters are same, the third characters still have to be sorted. So therefore, every time I'm looking at searching for something, I'm looking at the middle. I can divide by 2 and search for the C. Immediately, I'm going to find that C doesn't occur here. So my suffix array does not contain CAC. So searching is done by binary search over the suffix array. So we have this additional logarithmic factor coming from that binary search part. Other than that, so it's slightly slower to search, slightly slower to construct, but this logarithmic log n factor still may be comparable to that alphabet size we already have. All right, so it may be we may tolerate this logarithmic addition. As I said, its main benefit that people may prefer suffix arrays over suffix trees, the main benefit is its space efficiency and also ease of implementation, right? If I ask you to implement suffix trees, you're going to say, oh, it may be difficult. I need to have these dynamic, I need to implement a tree. But a suffix array implementation is very simple. All you need to do is sort your suffixes by using your favorite sorting algorithm, quick sort, merge sort, whatever it is. After you sort them, you get yourself your suffix array, and that's it. And then you may use it for searching for patterns. Yeah, so there is, I mean, this mlog construction is very intuitive. I mean, you just use it in any sorting algorithm you have. You will never use a quadratic running suffix array construction. Just sort the suffixes by using quick sort, merge sort, heap sort, whatever sorting algorithm you have. They are space efficient. The constant factor is slow, but there's an increase in query time because it will take, as I said, m log n time, m times log n time, where n is the size of your database, your original string that you're searching in. So there's this logarithmic factor, but this log function is very slowly increasing function. The logarithm very slowly increases. Therefore, for very large values of n, you may still tolerate this log n time addition to your query. Yeah, this is a pseudocode for searching for pattern suffix array. So we are searching for low and high. So we have a range. We are not looking for and pinpoint a pattern. We are always searching in ranges. At the end, this pattern search is going to return to us the low and high, 2 numbers. If a pattern exists in multiple suffixes in multiple places in a string, it's going to return as a result to a range, 2 numbers, the low index and the high index of our occurrence. We initialize this low to 0 and high to length of a. So without knowing anything, our pattern could occur in this entire array. And with each letter of our pattern, we are reducing this range to a smaller and smaller range. And at the end, so this binary searching is the place where it takes log n time. Yeah, search is in Mississippi. How do we search is in Mississippi? We first, for the first letter, we search for I. It reduces the index to 0 to 3. So the pattern, if is occurs, it should be here. Okay, now we search for letter S, and then the low and high, these indices become 2 and 3. So two suffixes, ISCP and ISSCP, contains the pattern is in as their prefixes. Okay, so this is how we find. It can be built very fast. It can answer queries very fast. For example, how many times ATG appears in a genome, you can find. So the ATG has a special meaning. It's the start codon, right? I mean, or methionine, or was it the stop codon? Oh, that's also true. The suffix trees and suffix arrays, we are using it for exact matches. So yeah, ATG is the start codon. Thanks for verifying, validating that. So we're in this course, in this introductory course, we just see suffix trees and suffix arrays for exact matches. We don't even allow mismatches. Okay, so no gaps, no mismatches. If you're looking, if you want to do exact matches, this is how you actually know how you can implement suffix arrays on your own to perform exact pattern matches. And there are variations of that to perform non-exact matches. It's also possible to do non-exact matches. There are probabilistic suffix trees, probabilistic suffix arrays. If you're interested in those, please search for the literature for those, but there are extensions of the original suffix trees and suffix arrays. But the idea is the main idea is the same. So this should be helpful for you to understand the material if you're going to need read those extensions. All right. Here are some links. Some of them may be outdated and they may not work, but just search. You'll get more. You'll get a lot of material on suffix trees, like probabilistic suffix tree. And there's actually, yeah, so there are different articles analyzing state sequences. Build a probabilistic suffix tree in R. So there is an R package, I think, PS tree, PST, probabilistic suffix tree. So you can take a look at these things. Variations on probabilistic suffix trees. There are even variations on that. This is a paper that appeared in Bioinformatics in 2001. So a 20-year-old paper is going to, I mean, if you're interested, for example, you can take a look at this one. Again, I found this paper by a Google search on probabilistic suffix trees. It's one, so you can also find it. All right. All right, that's it from me for today. I'll be happy to answer your questions if you have any. I will stop recording.